Good afternoon, everyone. Today I'm going to talk about rock forming minerals. So, this will be the outline topics that I'm going to discuss today. The first topic is crystal morphology. The second topic is cohesion properties. Under this are hardness of materials, fracture and cleavage, elasticity and plasticity, and tenacity. Topic 3 is optical properties of materials. Under this are macroscopic characteristics observable to the naked eye and examination of thin sections. And the last topic is geochemistry. So let's talk about crystal morphology. In crystalline structures, various planes with differing lattice densities intersect the axis of the unit cell at specific angles. As depicted in figure 5.6, which is the picture on our right side, these planes represent potential crystal faces, edges, and vertices. Steno's law, dating back to 1669, observes that equivalent faces of the same substance maintain constant angles, known as the law of the constancy of dihedral angles. Furthermore, in cubic systems, the most prevalent faces tend to be parallel to unit cell faces, or intersect them at a 45-degree angle, as shown in figure 5.9. Conversely, faces beyond these orientations are less common. Figure 5.10 illustrates the distinctive morphology of hexagonal systems, highlighting their unique symmetry and structure. So, let's break it into parts so that para mas maintindihan ng maayos. So, before that, I'm going to give you some definitions related to our topic. So ang external shapes ng crystals ay tinatawag na morphology. And yung arrangement ng atoms inside ng crystal ay tinatawag na crystal structure. And yung planes naman na minention dito, ito ay tinatawag na faces. Faces ng isang crystal or mineral. So ang crystals ay ito ay parang isang tiny building blocks na made up of atoms. And how these atoms are arranged inside, dito nakadecide kung ano yung physical look ng crystal outside. And ang crystal mayroong faces, just like how dice have sides. So ang ibang faces ay ang ibang faces nito are more stable than other faces. So this means they're more likely na mag-show up sa surface sa crystal. As indicated in the text, ang pinaka-common daw na face orientations in cubic systems are parallel to the unit cell faces, like squares or rectangles, intersecting the unit cell faces at 45-degree angles, like triangles and diamonds, and also faces with other orientations are less frequent dahil they have higher surface energy. In terms naman sa hexagonal systems, magkaiba. It's different. This hexagonal system is different from the cubic system we talked about earlier. Dahil ang hexagonal systems, mayroon siyang own unique na shapes and face orientations compared to cubic crystals. And also, ang hexagonal system, mayroon siyang special 120 degrees angle between sa dalawang unit cell axis, and yung third axis ay mayroong iba't ibang length. So figure 5.8. Figure 5.8 Figure 5.8 shows the 7 systems of crystal symmetry with shape and properties. So it has cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic, and triclinic. And together with its shape and properties. But before I proceed, let's go back here. So, this picture, pinapakita nito kung paano ang atoms nagla-line up in a cubic crystal. And yung lines pinapakita kung paano ang atoms naka-arrange. Kapag closer sa lines, ibig sabihin nun may atom doon. At may atom doon. And yung lines nag-meet sa horizontal, nag-meet horizontal and vertical lines at different angles. So, iba-ibang angles. And yung angles na yon pinapakita yung position ng atomic planes. So, like, line 1, it runs parallel to one of the axes. It means na maraming atoms sa direction na iyon. Just like lines 3 and 4, they meet the axis at a 45-degree angle. It means marami ding atoms sa direction na iyon. Sa line 5 naman, it makes a smaller angle with the axis. That's why it has a fewer atoms sa direction na iyon. So, overall, ang picture na ito pinapakita kung paano yung atoms nag-arrange in a cubic crystal, and yung iba't ibang direction ay may iba't ibang amount of atoms. And Steno's law mentioned na ang angles daw between corresponding planes are always the same. Like, it remains constant, wala gid na siya ga-change. No matter the crystal size. So, kahit maglaki yung size ng crystal, the angles between corresponding planes remains constant pa rin. So, figure 5.9. As you can see in this picture, yung arrow dito, yung arrow dito shows where the crystal grows fastest on its faces. Yung ibang faces nag-grow slower and maaring mawala eventually, shaping the crystal into a cuboid, which is this, cuboid. Ang cuboid system ay isang paraan ng crystals to organize themselves. It's defined by 3 different lengths for its axis, and lahat ng iyon nagmi-meet sa right angles. How atoms or molecules are arranged in the system, doon nagde-decide anong phases yung mag-grow and gaano kabilis. So, the arrows in the picture nag-represent siya specific directions sa growth, nag-represent siya specific direction sa growth na mangyayari sa loob ng crystal. The angles formed between crystal faces provide insights into the symmetry properties of the unit cell, helping determine the nature and symmetry system of the mineral. Crystal distances, which are usually multiples of the unit cell, can vary based on factors such as crystal size and growth conditions, influenced by pressure, temperature, and fluid properties. The environment in which crystals grow affect their shape and quality, resulting in either automorphic or xenomorphic crystals. Automorphic crystals found in flexible environments, like magma chambers or geodes, display well-defined, regular faces. On the other hand, xenomorphic crystals formed in solid environments like granite have less distinct faces, while identification primarily relies on automorphic crystals. Xenomorphic ones require X-ray diffraction techniques for structure determination. So, yung um yung angles between crystal faces nag-indicate sa symmetry of the crystal's unit cell. And nag-indicate siya sa yung angles between crystal faces indicate the symmetry of the crystal's unit cell. And yung distances between faces are often related sa unit cell size pero nagba-vary siya due to factors like size, pressure, and temperature. Yung crystals nagde-develop differently based on their growth environment and based on growth environment. Just like sa automorphic crystals, usually nag-grow ito sa environment where things can bend and change, like sa magma chambers or geodes. Mayroon silang nice and clear faces because mayroon silang space to grow without too many obstacles. So wala sila ga-face og daghan nga obstacles. They have space to grow. That's why they have nice and clear faces. Sa xenomorphic crystals naman, nagpo-form siya sa solid environments like granite, where kailangan nilang mag-compete sa space with other minerals. And dahil doon, they don't have such clear faces, just like how automorphic crystals. So in terms sa identification strategies, ang automorphic crystals, ma-identify siya directly using guides. While ang xenomorphic crystals, kailangan pa ng X-ray diffraction para i-analyze ang kanyang internal structure. And makikita natin sa figure 5.11 na ang automorphic crystals of apatite, itong AP, is surrounded siya ni biotite xenomorph. So the points na you need to remember is that mayroong two main types of crystal based on where they form, like automorphic and xenomorphic. So automorphic and xenomorphic, two main types of crystals based on where they form. So let's talk about twinning. Twins occur when identical crystals grow symmetrically connected by a symmetry element absent in individual crystals. This bond involves adjustments in orientation, such as rotation, usually 180 degrees, around a shared axis, reflection across a plane, or inversion around a center of symmetry. The twinning law determines the type of symmetry element and sets the crystallographic orientation of axes or planes. Resulting twins can have bonded contact or interpenetration. Twins may be simple, a few individuals, or polysynthetic, many individuals. While polysynthetic twinning, like that of plagioclase, is common, it's hard to observe without a microscope. So, ang twins, nangyayari siya kapag ang dalawang identical crystal nagro-grow together in a specific way. Just like sa examples figure na ito, yung Japanese twin, two quartz crystals joined along a shared face, with one crystal turned 180 degrees around an axis. Ito, 180 degrees. That's perpendicular to the face. That's why nagki-create siya ng V shape. As you can see, nag-create siya V shape. So, ang itong twin na ito ay tinatawag na contact twin. Dahil ang contact twin ay ito ay isang process na kung saan nagjo-join ang dalawang crystals together, either by touching each other or contact twins. Or ang isa naman, ito tinatawag na penetration twins. Dahil yung isang crystal pumasok sa isang crystal. Nag-penetrate siya sa isang crystal. That's why it is called penetration twins. So, ang twinning nangyayari when crystals grow together in a special way, joined by a feature that's not individual crystals. And yung crystals na nag-join can involve things like rotation, reflection, or inversion. So, ito yung mga dalawang examples ng twinning. So, these examples, pinapakita dito na how pinapakita kung saan ang twins can form and vary in appearance. Twins sila pero nag-vary sila in appearance. Like, magkaiba ng physical look. So, yung points to remember dito is yung dalawang yung twin. Type of twin. Contact twin and penetration twin. Contact twin is yung parang mag-touch sila together. And yung penetration is yung nag-penetrate yung isang mineral sa isang mineral. And it also says here na ang twins can be simple, involving just two or a small number of crystals. Pwede ring multiple. Ang tinatawag itong polysynthetic. Polysynthetic dahil nag-i-involve siya ng malaking number of crystals. So that's the points you need to remember. Cohesion properties. These properties are responsible for the mechanical strength of a mineral. They depend on the mineral structure and the forces linking the atoms. The first property is hardness of minerals. In 1822, Moss introduced a relative hardness scale comprising 10 common minerals for mineral identification. A scale still in use today. Higher numbered minerals scratch lower numbered ones when rubbed together. Intermediate non-mineral hardnesses include fingernail 2.5, knife blade slightly greater than 5, glass 5.5, and steel file 6.5. Mineral hardness aids in assessing mechanical strength and rock abrasiveness, although the relationship is intricate. Rocks with soft minerals are generally non-abrasive and weak mechanically. Conversely, rocks with hard minerals may be abrasive but not necessarily mechanically strong, dependent on mineral aggregation strength. Like for instance, quartz cemented sandstone is abrasive and hard, while calcite cemented sandstone is abrasive but mechanically weak. Consideration of rock abrasiveness is crucial for tool selection to prevent wear on machinery like tunnel boring machines and pumps, especially concerning the damaging effects of fine suspended quartz particles on equipment. So, ang question properties. So, ang question properties is tungkol siya. It talks about how strong a mineral is and ano yung nag-hold sa atoms together. Ang mineral strength nakadepende on how their atoms are connected sa kanilang structure. And nakakaapekto ito kung paano nila nare-resist yung scratches, breaking, and other physical damage. And para what they call that? Para um, ma-measure mo yung hardness mo, yung hardness ng isang mineral, most introduce hardness scale, which is naga-rate siya minerals from 1 to 10 based on how hard they are. So, gina-rate niya kung unsa ka gahi ang isa ka mineral. And, as we can see in this figure, 5.13, may numbering siya 1 to 10. And ang number 1, which is talc, is the softest. And yung number 10 is diamond, and which is the hardest. Hardness ay hindi lang siya yung only thing na nag-matter for a mineral strength. Like for instance, quartz, yung quartz, it might be harder sa calcite, but ang quartz cemented sandstone might not be stronger than calcite cemented sandstone. So nakadepende siya on how the grains are bonded. So, knowing a mineral's hardness, nakakatulong ito pumili ng tools na naglalast longer. Especially kapag nagdi-deal tayo ng minerals like materials like quartz. So the points that you need to remember here is that ang hardness of materials ma-determine using this scale, which is si Moss, which is inintroduced ni Moss in 1822. And meron siyang, it's ranked by 1 to 10. So, yun lang. Fracture and cleavage. To analyze a rock, geologists employ hammers to extract samples, revealing mineral fractures that can be random or planar. Aligned with lattice planes, cleavage donates fracture planes along which crystals preferentially break under mechanical stress, akin to cracks in a brick wall after an earthquake. Fractures fall into 4 categories based on cleavage number. First is crystals lacking cleavage break randomly, like quartz with conchoidal fractures resembling glass, just like this picture, 0 cleavage. Second, crystals with one dominant cleavage break into fine flakes, seen in polysilicate such as micas, which is this, 1 cleavage. Crystals with 2 cleavages form elongated prisms or fibers as seen in asbestos varieties. So, form siya elongated prisms. Fourth, crystals with 3 cleavages form compact prisms without noticeable elongation, like orthoclase and calcite, like this. Cleavage number and angle aid mineral identification using hand lenses or optical microscopes. Distinguishing between fracture planes and crystal faces may be challenging, but both indicate the same internal structure. So, in terms of breaking of rocks, ang mga geologists gumagamit ng hammers to break rocks and para pagstadihan. Dahil nakakatulong ito para malaman kung paano nagbe-break apart yung mineral sa loob ng isang rock. Ang rocks ay nagbe-break in different ways. Ang ibang fractures ay random lang, while yung iba nagpa-follow ng specific planes na tinatawag na cleavage. So ang cleavage nangyayari kapag ang minerals nag-break along certain planes due to their atomic structure. So to understand cleavage, para mas maintindihan yung cleavage, I'm going to relate it to earthquake. 'Di ba kapag may earthquake, yung mga walls natin may mga cracks. And yung mga crack na yun yung cleavage. So just like sa rocks, yung mga cracks doon, yun yung cleavage. Ang minerals ay mayroong iba't ibang numbers ng cleavage planes. Like for example, yung mga walang cleavage, nagbe-break sila randomly. While yung mga one cleavage lang, nagbe-break into thin flakes. So yung number of angle ng cleavage planes nakakatulong mag-identify ng minerals. So the important points here is that na kapag para mag-extract of examples, ginagamitan ng geologists, gumagamit sila ng hammer para i-extract yung samples. And yung cleavage, ito yung crack sa rock. And may apat siyang categories based on cleavage number. Kapag walang cleavage, kapag lacking siya ng cleavage, nagbe-break siya randomly. Pag one dominant cleavage lang, break into fine flakes. Kapag dalawa, mag-form ng elongated prisms or fibers. Kapag tatlo naman, bumubuo siya ng compact prisms without noticeable elongation. So, yun lang. Elasticity and plasticity. When subjected to mechanical stress, minerals exhibit deformation ranging from elasticity, reversible, to rupture, with an intermediate plastic stage, reversible. Mineral response to stress varies depending on bond type. Understanding these mechanical properties is crucial, especially in the context of rock deformation. So, yung elasticity, ito yung minerals na nagbe-bend temporarily under stress but bumabalik sa kanyang original shape. And ito ay parang isang rubber band. Kapag in-stretch mo yung rubber band, bumabalik. Nagsasnap back yung rubber band. So that's how elasticity works. Yung plasticity naman, ito yung mineral na nagbe-bend in a way na hindi siya bumabalik sa kanyang original shape. Or so kung ano siya before, hindi siya mababalik even though na wala na yung stress. So next, tenacity. Mineralogists employ specific terms to characterize mineral behavior under mechanical tests. Fragile or brittle, easily broken or pulverized, malleable, can be hammered into sheets, sectile, can be sectioned with a knife, ductile, can be drawn into wire, and flexible, pliable but doesn't revert to original shape. It's understandable naman. Ang tenacity is another way siya to talk about how minerals act kapag tinetest. Like yung sinabi dito, kapag fragile siya, masisira siya ng madali na siya masira or mabroken. Kapag malleable naman, magiging turn into sheets. Kapag sectile naman, can be pwede siyang makat with a knife. Ang ductile naman can be pulled into wires, and yung flexible, nagbe-bend but hindi na bumabalik sa kanyang original shape. Optical properties of minerals. The atomic structure or chemical composition of a mineral gives it specific optical properties that can be used for field identification. Characteristics visible to the naked eye or through the hand lens, such as luster, transparency, and color, are used for identification. So, ang geologists gumagamit ng optical properties to identify minerals. The way atoms are arranged sa mineral, or what the mineral is made of, gives it special optical features. So, things like kung gaano siya ka-shiny, ka-transparent, or colorful, ang mineral, nakakatulong ito katulong ito para i-identify ang mineral na ito. Whether we're looking with our eyes or through hand lens. So, mayroon siyang characteristic visible to the naked eye through Hardness as luster, transparency, and color. So, itong tatlo, ito yung nag-a-identify. Macroscopic characteristics observable to the naked eye. First is reflectivity, luster. The reflectivity of a mineral is the ratio of reflected flux to incident flux. It directly influences the luster of a mineral. Metallic luster, as shown by the sulfides, is distinguished from non-metallic luster. In the non-metallic category, there is vitreous luster, quartz, feldspars, adamantine, diamond, resinous, sulfur sphalerite, greasy, chalcedony, silky, gypsum, pearly, micas, porcelaneous, and earthy. No luster because it is an aggregate of small, variously oriented grains. So, ang macroscopic characteristics ay ito yung bagay na makikita natin using our eyes. So, ma-observe natin ito using our eyes. Like yung mata talaga natin. And ang reflectivity is, ang reflectivity is how much light bounces off compared to what hits the mineral. Nakakaapekto ito sa pagiging shiny ng mineral. Like kung gaano ka shiny yung mineral. Minerals can be shiny like metal, metallic luster, or not like metal, non-metallic luster, such as glassy like quartz and resin-like like sulfur. So, ito yung mga examples. Quartz, feldspars, diamond, sulfur, chalcedony, gypsum, sphalerite, and micas. Next is transparency. Transparency in minerals refers to the extent to which light can pass through them. A mineral is deemed transparent if an object's details can be observed through it. Translucent minerals allow some light to pass through, though not entirely, resulting in a partially obscured view. Most rock-forming minerals, notably silicates, fall into this category. Conversely, minerals that completely absorb or reflect light from the surfaces are classified as opaque. Typical oxides and metallic sulfides. So as we can see in these three pictures, ito yung transparent. Ito yung naglalet ng ito yung mineral. Makikita talaga natin like ang details. Kasi nga transparent. Objects seen through rhombohedral calcite. And so, even though na isang line lang yung isang bagay lang ito, pero with this mineral, may makikita tayong dalawa. This is because of double refraction. Sa translucent naman, inaalaw niya yung light to pass through, but not entirely. Just partial. Makikita nyo naman dito sa example. Ang opaque naman, hindi niya inaalaw yung light na mag-pass through sa kanya. Dahil, ina-absorb niya or nire-reflect niya lang ito. Hindi niya pinapapasok. So, makikita na yung differences ng tatlo. Ito, very detailed. Makikita talaga transparent, very transparent. Makikita talaga natin yung object, which is this. And translucent, may makikita tayo pero konti lang. Because, dahil hindi entirely na pinapapasok yung light sa kanya. And yung opaque, wala talaga. Kasi, nire-reflect niya lang or ina-absorb niya ang light. Next is color. So, color is another important clue. Nangyayari ito kapag ang specific colors of light are are soaked up or reflected by the mineral. So, ang ibang minerals, may colors, they are because they link to what they are made of. So, kung sa ano sila gawa. So, may characteristics, three characteristics ay may types of coloration. May three types of coloration. Characteristic color, directly associated with the coloring element in chemical composition. Crystal structure, inclusions, and optical phenomena like reflection and refraction. Coloration due to anomalies. Colorless minerals may appear colored due to imperfections in the crystal lattice, such as the replacement of atoms of different valence. Coloration due to impurities, trace chemical elements. Trace chemical elements can impart color to minerals. Quartz, normally colorless, may exhibit various pastel hues like mauve, iron, pink, and red hematite. So, some minerals have colors linked to what they're made of, like yung sa greenish yellow for Fe2+, or reddish for Fe3+. Yung iba, nagmumukhang colored because of yung iba nagmumukhang colored dahil sa kung paano kung paano ginawa yung crystals or ano yung mga tiny chemicals na nasa loob dito. That's why may makikita tayo na iba na may colored, and these are the reasons. For as what I've said earlier, dahil ito sa kung paano sila ginawa or may mga tiny chemicals pa doon sa loob nito. Sorry. Para ma-identify natin yung tunay na color ng isang mineral, we scrape it on a porcelain plate. For example, ang hematite makes a red mark while ang magnetite makes a black one. As we can see in this picture, nagsho-show ito ng minerals with special colors because of certain chemicals. Like sa manganese, nagkakause ng coloration in rhodochrosite, and ang uranium nagkakause ng yellow color of autunite. Examination of thin sections. Optical properties that are challenging to ascertain with the naked eye or a hand lens can be thoroughly examined using a polarized light microscope to determine a mineral's identity. To identify a mineral under such a microscope, a thin section is prepared by fixing a small rock tube to a glass plate and reducing its thickness to micrometer, 30 micrometer, hence the term thin section. Examining the thin section under an optical microscope with light below it allows us to distinguish between opaque and translucent minerals. So, kapag kailangan natin tingnan ng malapitan kung kung paano nag-interact ang mineral sa light, especially yung mga may hirap makita with our eyes or regular hand lens, gumagamit tayo ng special tool na tinatawag na polarized light microscope. So, para ma-figure out what mineral is using this microscope, we make something called a thin section. Ibig sabihin nito na we stick a small piece of rock sa isang glass plate and ginagrind ito until na maging super thin, just 30 micrometers thick. That's why tinatawag itong thin section. So, translucent minerals fall into two categories. Optically isotropic minerals. These include non-crystalline minerals like opal and cubic system crystals such as halite and fluorite. Light propagates uniformly in all directions, characterized by a single index of refraction. Second, second category, optically anisotropic minerals. These minerals belong to other crystal systems and exhibit varying light propagation velocities depending on the angle of incidence. They possess infinite indices of refraction between the extreme values of the ordinary and extraordinary rays, a phenomenon known as birefringence. Most minerals are anisotropic to varying degrees, with calcite being highly anisotropic and quartz less so. So, kapag nagche-check tayo sa thin section under microscope with light beneath it, we can tell apart two kinds of see-through materials. First is yung, as mentioned dito, optically asotropic minerals. Ang minerals na ito, wala siyang regular na crystal shape. And ito ay nabilong sa crystal system na tinatawag, tinatawag na cubic. And ang light dito na gumagalaw the same way in all directions through these materials, and mayroon lang silang one-way light bends. Ang optically anisotropic naman, ito ay isang mineral na belong sa other crystal systems, and ang light dito nagmo-move at different speeds. So, different speeds nakadepende sa angle depende sa angle na it depends on the angle it hits them. So, itong tinatawag nating birefringence, ito yung kung saan ang light nag-split up into two rays with different speeds. So, most minerals are like this in some ways. Key points nito is two categories, optically isotropic minerals and optically anisotropic minerals. And yung ginagamit dito to examine this mineral is called polarized light microscope. So, figure 5.16. Display of calcite's high birefringence, the object seen through the rhombohedron is doubled. One of the images come from refraction according to the index of refraction, and the other one comes from, thus calcite has a negative birefringence. So, as we can see dito, it looks strange because you only have one line here, but dito, two lines. Tas, two lines dito, din dito. So, when we look at this object through a piece of calcite shaped like rhombus, ang object, it seems like it's in two places at once. Nangyayari ito dahil sa light na dumadaan, passing. Nangyayari ito dahil sa light na nagpa-pass through calcite and split niya ito ng dalawang two beams split ito into two beams. That's why two beams in different speeds. So, magkaibang speed. Hinati sa dalawang beams in different speeds. This is also because nag-change yung calcite's index ng index of refraction ng mineral na ito. Yung one beam ay galing sa highest index of refraction and makes one image. This one image. And yung isa naman, galing sa lowest index of refraction and make another. So in calcite, this difference gives it a negative birefringence of negative 0.172. As we can see in figure 5.17, we can see that the path light takes through a polarizing microscope. So 5.17. Trajectory of light waves through a polarizing microscope with the polarizes in perpendicular position. If the mineral is anisotropic, there is no extinction. The observer perceives a color that depends on the birefringence of the material. So, when a mineral is anisotropic, ibig sabihin, ang properties nito nag-change depending on kung saan ka, on which way you look at it, depende kung saan ka tumitingin. And hindi siya, it doesn't go dark when you turn the filters. Instead, yung mga observer, nakikita nila na ang colors, and yung mga observers na may nakikitang colors, depende on how much the mineral's light splitting properties vary. So, I hope you understand that. So this is the analyzed polarized light. The thin section, the thickness is 30 micrometer. Light polarized in a plane. First polarizer, non-polarizer light, and ang light source. Geochemistry. So this will be our last topic for today. Before examining the principal minerals from a geochemical point of view, we shall define several essential notions linking the physical structure of a mineral to its constituent elements. Substitution in minerals follows strict rules based on ionic radius and electronegativity. Similar atoms can replace the principal atom without altering the structure significantly. For instance, replacing silica in aluminum silicates alters the silicate group's charge, allowing the introduction of a monovalent cation. Substitution may occur accidentally, leading to changes in color but not the mineral's fundamental properties. For example, corundum is colorless, but with Cr3+, it becomes red, ruby, or blue with Fe2+ or Ti4+ sapphire. Systematic substitution of atoms with similar ionic radii leads to solid solutions. Continuous solid solutions allow all proportions between extremes, seen in the plagioclase series, while discontinuous series like alkali feldspars have limited compositions. In mineral formulas, the substituted atoms are denoted in brackets. Let's hatiin natin para mas maintindihan. So, ang geochemistry, ito ay isang study of how minerals and rocks form and paano sila nag-interact with the Earth's environment. So, ang substitution is a big idea in mineral chemistry. So, yung sinabi dito na similar atoms, sometimes atoms with similar sizes and electron attractions can take each other's place in a mineral structure. Pero hindi niya pinimess up yung mga bagay. Hindi niya, kung ano yung sinabi ito, hindi niya, wala siyang sinechange na mineral's fundamental properties. So ang pag-swap ng atoms can change a mineral's electric charge. So binabago niya yung electric charge. Yung swapping of atoms, binabago niya yung ang electric charge ng isang mineral. And para mabalance ito, need natin to add another extra atoms para magbalance. to balance it out. So, minsan, ang pag-swap ng atoms nagbibigay ito sa minerals ng pretty colors. Just like sa na-mention dito, like ruby and sapphire. Kapag ang similar size atoms nag-swap, it can make a solid solution where mayroon itong range of possible mixes. And makikita natin ito sa plug-clay series and alkali feldspars. In terms of notation naman, in mineral formulas, yung swap atoms are kadalasan na pinapakita in brackets to give hint at their variability. I hope you understand my explanation. Polymorphism. Polymorphism refers to the ability of certain mineral substances to exist in two stable crystal forms under unique pressure and temperature conditions. Carbon, for instance, can manifest as diamond, cubic system hardness of 10, or graphite hexagonal system hardness of 1. The formation of these structures occurs under vastly different conditions. Diamond under high pressure and graphite under moderate pressure. The boundary between diamond and graphite lies approximately 50 kilometers deep. Exploring the minerals fundamental to rock formation, we classify them by geochemical families. Each mineral group is presented with its chemical composition, typical appearance, physical properties, natural environments, and technical application. So, polymorphism, ibig sabihin nito, ang minerals nag-i-exist in different crystal forms. So, nangyayari ito because pwede niyang i-arrange yung atoms in different ways, in various ways, depending on how it forms. So, itong tinatawag na different forms ay tinatawag na polymorphs. And pwede ito magkaroon ng different properties like hardness and color. So, like dito yung example niya, carbon, pwede siya magkaroon ng dalawang polymorph. So, pwede siya mag-manifest as diamond, cubic system, hardness of 10, and yung graphite, hexagonal system, hardness of 1. Another example of this is calcite. So, ang calcite is a mineral made of calcium carbonate. And pwede siya magkaroon ng dalawang polymorphs, calcite and aragonite. Silang dalawa ay mayroong same chemical makeup, CaCO3. But nagkakaiba lang sila sa structure. Ang calcite is common na makikita sa limestone and marble, while yung aragonite is nakikita sa pearls and seashells. So, yung conditions during sa formation, like yung pressure and temperature, decide which polymorph is stable. So, ito yung nag-decide, yung pressure and temperature nag-decide kung anong polymorph yung stable. So sa calcite, gusto niya ng low pressure and temperature, while yung aragonite, mas prefer niya ang high pressure and temperature. Just like here, ang diamond is under high pressure and graphite, pero yung graphite is under moderate pressure. So, back to calcite, when you heat calcite, pwede siyang mag-turn into aragonite. So, yung iba't ibang polymorphs nag-i-indicate ng conditions kung kailan nagawa yung rock, kung kailan ito ginawa. So dito, even though pwede siya magkaroon ng dalawang polymorphs, pero nag-differ naman siya sa structure. sa structure niya. Sa structure. So, I hope you understand my explanation. So, yung ang different forms, let's balikan natin yung polymorphs. Ito yung mga different forms. And yung polymorphism is, ito yung mineral na pwede mag-exist in different crystal forms. Just like sa binigay na example. I hope you understand I hope naintindihan yung mga sinasabi ko. So, this ends my discussion. I hope you understand it, and thank you for listening.